last time on Wince versus Susskind.
This is a formula which was based on an assumption, the assumption being that time is universal. That's what Einstein found was wrong. When you're in a moving frame of reference, two different observers will not agree about what time a particular event takes place.
Einstein failed to capture with relativity that at the edges of relativity itself, motion is better described using an infinite series of relative frames of reference, and the time variation transformation from existence must be applied. What we basically get is a new equivalence principle that allows for the invariance between space and time.
Now, does that mean that space has become time and time has become space? No, it just means that the coordinates are doing something funny.
We're just going from a spatial coordinate system to a temporal coordinate system, passing through the origin, where they come together and preserve the Pythagorean theorem.
They would have to be corrected in moving frames.
The Lorentz transformation has been used to calculate the variance in relative time.
The physicist interested in light beams would have to correct things for the motion of his reference frame. Now, it's an experimental fact that this is not the case, that you don't have to correct for motion. It was the famous Michelson-Morley experiment.
Unknown to the experimenters, in our example, there is an unaccounted for aspect to this paradox, given that A and B exist in relative frames of reference, using the existence equations as a calibration to the Lorentz transformation. And the twin paradox gives us this result. B has descended down the y-coordinate of time. Therefore, B now travels in the x-coordinate direction slower than it previously did. What ends up happening is A and B are using the conventional Lorentz transformation to calculate their own twin paradox situation.
If I Lorentz transform it, after the Lorentz transform, it will still be on the same hyperboloid.
Both A and B are at the temporal midpoint of the time it takes for B to return. So what we have is a failure of special relativity. For a brief second, these guys are completely mystified because both have a time displacement centered around the linear time of the common event, regardless of who travels.
So from Bob's perspective, he sees Alice asymptotically approaching this line. What will Alice see? Yeah, she just looks back and she sees somebody. Okay, keep in mind there's some asymmetry here when you talk about what Bob sees and what Alice sees. Let's draw the diagram again.
Therefore, when B finally arrives at A saying, "Sorry, I am late," A looks at his brother with astonishment and says, "You have arrived early." To both of their surprise, the clock that B took with him reports that B took longer to arrive than predicted. Also, the clock that A had with him reports that B has arrived ahead of schedule.
What a crowd we have here with us tonight. Unbelievable. The round is about to start. Who will win?
As a review, let's see what the motivating factor for this little video series was.
The question of whether or not when you see something, you see only the light or you see the thing you're looking at is one of those dopey philosophical things that an ordinary person has no difficulty with. Even the most profound philosopher, in sitting eating his dinner, hasn't any difficulty making out that what he looks at perhaps might be only the light from the steak, but it still implies the existence of the steak, which he's able to lift by the fork to his mouth. The philosophers that were unable to make that analysis and that idea have fallen by the wayside through hunger.
He was a philosopher.
Oh, really? Philosopher, huh?
Richard Feynman was also a showman, an enormous showman. He was full of macho, a kind of macho one-upsmanship. He loved intellectual battle. He loved to win. When these little macho games that we would sometimes play, and he didn't only play them with me, he played them with all sorts of people, he would almost always win. But when he didn't win, when he lost, he would laugh and seem to have just as much fun as if he had won. Dick and I would meet a couple of times. We met a couple of times up in San Francisco at some very rich guy's house, up in San Francisco for dinner. And the last time the rich guy invited us, he also invited a couple of philosophers. These guys were philosophers of mind. Their specialty was the philosophy of consciousness. And they were full of all kinds of jargon. I'm trying to remember the words. Monism, dualism, categories all over the place. I didn't know what those things meant, neither did Dick. But the trouble with the philosophers is that they were philosophizing when they should have been scientifiizing. It's a scientific question, after all. And this was a very, very dangerous thing to do around Dick Feynman. Feynman let him have it, both barrels, right between the eyes. It was brutal. It was funny. Ooh, it was funny. But it was really brutal. He really popped their balloon.
Okay, well, I'm in full agreement. Yes, we should definitely do more scientifiizing. So let's proceed. Let's examine the Minkowski diagram, where Susskind is showing the use of the unit hyperbola diagram in special relativity for showing the relationship of space and time with time dilation, etc. We'll go ahead and draw a regular xy plane, this being y, this being x. And what we've seen is that Susskind is using more or less 45-degree lines to represent the speed of light. In this diagram, that would be y equals x for this line. And the hyperbolic coordinates that he's been drawing like this would correspond to the equation 1 equals x squared minus y squared. And then over here, these coordinates, the conjugate of these coordinates would correspond to the equation 1 equals y squared minus x squared. And this is the unit hyperbola graph that is used in general and special relativity. And basically all we have to do is swap out x and y throughout the rest of this for s and t. And we end up with what we've been seeing Susskind use for the past few rounds. Before we move on, I want to point out here that there's something kind of, there's a mix-up in the way that Suskind's using his metric with the coordinates that he doesn't necessarily point out, at least in the way that I've presented his material, that I need to point out real briefly so that there's no technical issues. That being that the metric here in this equation is what we would use corresponding for our 3 dimensions of time. So that would be the derivative of tau for time equaling the derivative of space squared minus t plus t1 squared minus t2 squared minus t3 squared. And that this would correspond to what Susskind has been using, dt for space squared equals t squared minus x squared minus y squared minus z squared. Now, as you can see right away, the problem is that this corresponds with the conjugate having to do with time rather than having to do with the spatial coordinates, and he's been dealing with the spatial coordinates rather than the time coordinates, even though he's kind of going back and forth. So I'm not quite sure if he points that out in one of his other lectures, but I need to point it out here so that as we move on and show where the complex conjugate and the three dimensions of time relates to the Minkowski diagram, that this issue won't appear to be a technical problem that I'm making. So, moving right along. Again, this is 1 minus t squared, I'm sorry, 1 equals t squared minus s squared for the conjugate of 1 equaling s squared minus t squared. So let's go ahead and draw the Minkowski diagram with the three dimensions of time applied to it and see what the existence equations applied to the Lorentz transformation looks like graphically in relation to the Minkowski diagram. So we'll go ahead and draw our time-space coordinate. This representing space, this representing time. We'll use red for our asymptote line representing speed of light equaling 1. And we'll use blue. We'll use blue for the hyperbolic trajectories that correspond to B, Bob in Suskind's example, and we'll use this hot pink color. I'm first going to draw this one. We'll use this hot pink color here for the hyperbolic curves corresponding to A in our example, or Alice in Suskind's example. And so the question is, where do the three dimensions of time go? Susskind points out that the three dimensions of space are sort of sticking out of the whiteboard and that we're not going to pay attention to them. So let's go ahead and just ignore the extra dimensions of space for a moment and figure out, okay, so now we've got extra dimensions of time sticking out of the chalkboard. What do they look like? Real quickly, let me go ahead and just finish this. And what I'm going to propose to you is what I've been suggesting before, is that the very elusive present dimension of time is sticking out of the whiteboard directly at you or me or whoever's looking at this. So it's a little harder to see and comprehend. So what we'll do is we'll go ahead and take this paper. First, let's go ahead and draw our extra temporal dimension here. So this will be T1 now. We'll go ahead and make this T2. And so we'll go ahead and pop our present dimension time out of the whiteboard here. Hope that looks all right. And so now this is getting pretty interesting. So we can see that rather than Alice crossing some line, having the determinant cross 0, the metric change sign, and basically special relativity fail, what we can do with the extra dimensions of time is sort of keep Alice sort of stuck in space-time where she can't get out of space-time. So the question is, okay, well, what happens as Alice leaves the trajectory, right? So in Suskind's example, we see Alice. She sort of just drifts off the trajectory at some point. Actually, this is a better way of drawing that. She drifts off the trajectory at a point like this, and what Bob sees is as he continues down the hyperbolic line and continues making observations of Alice, he sees her slowing down more and more and more. Well, of course, because what she's doing is Alex is actually transitioning with a hyperbolic curve corresponding to the asymptote of the speed of light, but now in relation to 3 dimensions of time. And so we now have an asymptotic curve like this, or a hyperbolic curve like this. It's almost like taking the Minkowski coordinate system and rotating it this way. And so we have it like this with our coordinate like that. And so what's happening is Alice is actually just getting more and more into the direction of the present time. So what you could think of then is that if you were to think of this as, again, the present time, think of this as linear time, if you were to, or actually let's go this way to go with our graph here. If you were to come this way, right, as you're coming this way, and then you're slowing down, what you're actually doing is you're actually transitioning onto more and more and more of the present time dimension coordinate. So that what happens is relative to Bob, when he gets way down his hyperbolic trajectory, and Alice more or less appears to be standing still, relative to Bob, Alice is actually now pretty much positioned along the present time coordinate. And so that's what we're having here, like this. So rather than her crossing the line and having to do a mathematical trick and a bunch of hand waving at, around the determinant at 0 and the metric changing sign, we simply just add extra dimensions of time and trap Alice within space-time. And at this point where it appears that she's going slower and slower and slower to Bob, she's actually just transitioning down the present time coordinate. Okay, I've gone ahead and written out the equations. So when we take our 3-dimensional time coordinate system, remember period for ordinary linear time, present, and that we could rotate it either way, that we could have periodic moments of the present time, or we could look at it as a continuous present through a series of periods, all being either the same period or a different period. So coming out of this trajectory, these would be more or less different rates of the passage of time, except these would be different rates of time linearly, and then this coordinate corresponds to how those can be different in relation to each other. So two observers could experience the same trajectory, but one at a faster rate than the other. So again, period, present, and passage, these being our 3 dimensions of time. So what with our Minkowski diagram, what we have is this being present, or I'm sorry, this being period. So let's go ahead and rotate it this way to match up with this coordinate of the present here. And then let's go ahead and tip it this way so that our T1, our period, corresponds to T1 in the Minkowski diagram. And then, as we take this and pop it out and rotate it out this way so that the present dimension of time is sticking out of the whiteboard, we rotate our coordinate system here so that we have T1, T2, and T3. Now something I want to note which we'll bring up at a later point, is notice that the passage of time coordinate has a one-to-one correspondence with the spatial coordinate. That's very significant, and we'll bring that up later. The main point I want to show here is just how easy it is to apply 3 dimensions of time to the Minkowski diagram and more or less get the array of equations that we've written. So I'll go ahead and put this down and go over those. Here we have the hyperbolic equation that would correspond to T1 and T2, which I demonstrated with the little wooden diagram. Here, this would correspond to T2 and T3, which I also demonstrated with the little diagram. And so through either complex conjugation or simply just adding an extra time dimension, what we get is T1 squared minus T2 squared minus T3 squared, the 3 dimensions of time, and from that, by bringing in the spatial time coordinate orthogonally to our 3 dimensions of time, this is how we get this equation, the derivative of tau for time squared equaling the negative derivative of space squared plus the derivative of time t1 squared period minus t2 squared present minus t3 squared passage. These 2 extra dimensions of time is what would account for something where, let's say, oh, I don't know, we have a particle that has a small enough mass, I can't think of anyone right off the top of my head, but let's hypothesize a particle that has a very small mass. It's possible one could see with the whole issue of something going past, of a particle, moving fast enough and having mass, a slight enough mass, that particle could be measured in such a way that a conundrum might arise where the particle appears to be moving faster than light, when in fact it isn't, because all it's doing is moving along these 3-dimensional coordinates, which are here. So right away, with applying the 3-dimensional coordinate system to the Minkowski diagram, one intuitively would come up with the concept of, well, we should look for particles moving near the speed of light and see if we can measure them in any way whereby they may appear to be traveling faster than they are. And if you refer back to the application of the existence equations to the Lorentz transformation in the adjusted twin paradox, that's where that reasoning would come from, because what it is that the length of the trajectory of A, if you will, along this curve, if it's laid out flat like this, right? So if we take a curve like this that would represent A moving along a trajectory of 3-dimensional time having to do with relative frames of reference between Bob and Alice, etc., etc. Please refer to round 1 through 3 for all of that. If we have A traveling along a curved trajectory, but we're using a mathematics assuming that she's moving along a flat trajectory, and in our mathematics, we basically, could project that this is where A is going to be. Well, if you roll out this curve flat, it ends up actually being out here. And so this little extra length here in the existence equations, which for A would be n star minus I, which is added to A to give us A star, is accounting for this extra length in a curve having to do with the trajectory of A relative to B following an additional hyperbolic set of coordinates corresponding to 3 dimensions of time. And real quickly, if you remember, I'm out of space here, but if you remember, the metric for d tau time squared, our metric is -1, 1, -1, -1. And for Susskind, in special relativity unmodified with the existence equations, he uses the derivative of tau, make that look a little better, derivative of tau, but what I'm calling tau space squared, that its metric is 1, -1, -1, -1. And so what I showed in round 3 is how when something is approaching, crossing where c equals 1, that rather than doing a mathemagic trick, what we can actually do is just use this three-dimensional time coordinate system, this particular metric, which the eigenvalues that we get from over here, and the complex conjugation and all that business, when that comes out here, that's how we get the eigenvalues here for this metric. And what you can see is that, I'll go ahead and write the other one over this so that we can see what I'm talking about. D tau space equals, here let me erase this so we can make that much more clear. This is actually a pretty significant thing to point out, that the derivative of tau space squared equals the derivative of time squared minus derivative of x squared minus derivative of y squared minus the derivative of z squared. And this is where he gets the eigenvalues for the metric 1, -1, -1, -1. And if you recall, in round 3, he had an issue with when rho, using polar coordinates, when rho approached the origin, what the problem was is that the time and spatial coordinates flipped, and he made a big deal about that being a problem. Well, if we're using 3 dimensions of time and 3 dimensions of space and have them interleaked in this orthogonal manner, what we end up having is that you can see, no, the metric is not, it looks like the metric's changing sign, but it isn't. It's that the time coordinates, I'm going to more clear here, here's the time coordinates here, right, time there, and these spatial coordinates here and here. The spatial and time coordinates are interchanging, yes, because we're switching from moving along one hyperbolic trajectory to another. So yes, we can have variance, we can switch from one hyperbolic curve to another, and instead of that leading to an infinite regress, the existence equations show at this point pretty much unarguably how to deal with that. And it even suggests ways that we could even make a prediction for situations when we would have a particle, say something with mass but light enough that it moves in nearly the speed of light, that we should start to see a situation where we could measure it in a traditional manner and get a result that makes it looking like it's going faster than light. Before we move on, and I don't want to pump myself here, I taped the little wooden coordinate deal onto the whiteboard. I don't know if you can see it or not, but that's to represent how we've juxtaposed the 3 dimensions of time onto our Minkowski coordinate system. You see this sort of turquoise column tried to draw here, that's to represent how we had this flipping out, sort of with the corresponding with this coordinate here. So you could sort of imagine all of this that you're seeing on the whiteboard here coming out this way, but I've laid it flat so that we could examine it. So these would be the hyperbolic coordinates that A, I'm going to write these down. That's A, and then this is B. What we're arguing is that special relativity is what we're arguing is that relativity is incomplete, that the 3 dimensions of time added to relativity in the manner that we have shown completes relativity, and that what we need to do is have these extra hyperbolic coordinates to correspond to Alice, or A if you will, relative to Bob, and that the coordinates of Bob relative to Alice weren't sufficient. And so here we have remember the present dimension of time, which is sticking out of the whiteboard at us, or you more or less, present dimension of time, and passage moving along the same direction as the spatial coordinate. That becomes quite interesting later. And then here we have our 45-degree line corresponding to the speed of light equaling 1. So, what I'd like to point out is this section pulled out of our 3-dimensional time coordinate system, if you will, and laid flat here. This being period T1, and this being present, a present moment. Now what's assumed is that the speed of light is the same in all reference frames. I don't have a problem with that. In fact, I believe that that is absolutely true, that the speed of light is the same in all reference frames. However, what I'm going to argue is that not all reference frames correspond to one another in such a way that if you take the measurement of the speed of light from one uniformly accelerated reference frame and compare it to another, that you're going to have a correspondence between those measurements using the Lorentz transformation in its current form, and that we need to apply the existence equations as a calibration to the Lorentz transformation to account for that little extra aspect of relative frames of reference, ironically, to preserve that the speed of light is the same in all frames of reference. So in order to preserve invariance, we actually have to allow for variance, but in a very specific place. So again, T1, T2, so if the speed of light in the present time, unadulterated, if you will, by observation, then what we have, applying the extra dimensions of time, is you can see it as that the speed of light in the frame of reference of Alice is slightly faster than the speed of light is without any relative frames of reference, and not for Alice, but for Bob. So because Bob is in an accelerated frame of reference, and because he's making observations of Alice, even though Alice herself is not in an accelerated frame of reference, Alice relative to Bob is. So that's what this modification to the angle of 45 degrees alpha is to account for n star minus I, or the speed of light in Alice's frame of reference relative to Bob. And then beta would be moving slightly down, such that the speed of light in Bob's frame of reference is slightly slower than it is for Alice in her frame of reference. So the irony is yeah, the speed of light is the same in all frames of reference, but the frames of reference themselves differ. So once we account for this slight variation in the relative frames of reference, which delineate into a three-dimensional time coordinate system, and when we apply it here, what we need to do is change the speed of light from 1 to the identity constant in the existence equations, and then we subtract from or add from the identity constant, and that's how we calibrate the Lorentz transformation for the relative frames of reference. And for instance, with the superluminal neutrino, if we were to take the superluminosity, if you will, of the neutrino and apply it to these equations, or apply these equations rather to the superluminal neutrino, what you end up with is finding that the neutrino did not move faster than the speed of light. It's just that it turns out that the Michelson-Morley experiment is actually slightly incorrect, and this CERN experiment using the satellite to measure the lengths of time it takes for the neutrino to travel from one detector, from the emitter to the detector, more or less, that what that shows is that the Michelson-Morley experiment held true enough in a small enough experiment for relativity to be discovered, but the situation with the superluminal neutrino opened our observation enough to see that actually we need to go all the way back to Newton and refine that even more, use Leibniz's version of more of an interactionism-based relative frames of reference model for the calculus, come forward, and ta-da! Everything works as normal, with the exception that we have this peculiar situation happening where, well, look to Wince versus CERN. I'm now going to introduce the Vinczian, which is more or less a coordinate system of either the dot product or the cross product of vector spaces, those vector spaces being the spatial vector space, the temporal vector space, and the observational temporal space. So over here we can see it. We've got our 3 dimensions of space, we've got our 3 dimensions of time, and we have, what we'll learn much, much later, are our 3 dimensions of observation. Real quickly but simply, I've got 3 here, but the minimum could be 2, and then the third being units. So we have an observer, something being observed. There could be even another thing observed or what have you. But within that, we have our units. And you could think of this complex vector space as having to do with this complex vector space and this complex vector space in sort of a cross-product manner. So this vector space, this complex vector space here, corresponds to relativity in quantum mechanics traditionally. Here we have our 3 dimensions of space with our 1 dimension of time times the speed of light, and I representing imaginary number for representing the orthogonal relationship of space and time. Over here, similar thing. We have our 3 dimensions of time. We have the speed of light and space rather than time, times I for the same reason as we had over there. And then up here we have observer 1, observer or observee 2, observer or observee 3, and then whatever space-time coordinates we're using between this observer and this observation. And the observation complex vector space corresponds to issues with Kant, Descartes, Newtonian mechanics and Leibniz issues. So we have, and then again the three dimensions of time, corresponding space, we use the existence equations. So all of this together represents the Vinczian, which equals the complex vector space of observation with the cross product of the complex vector space of space, cross product, complex vector space of time, or same thing with dot products. And this could be reduced even simpler to where we're not even using vector spaces, we're actually just using vectors. But that, again, would correspond more to this observational thing. Point of this is that the relationship of objective and subjective frames of reference can be shown quite easily here, to where the objective frame of reference obviously corresponds to space with one dimension of time. Relativity and quantum mechanics do quite well for describing the objective frame of reference. And then the existence equations, which bring up the issue of the subjective frame of reference. Clearly, the three dimensions of time and the one dimension of space correspond to the subjective frame of reference. So here we have now applied in physics the subjective frame of reference, and we've given some examples of how the issue possibly with this neutrino could be used to show that this mathematical coordinate system is correct, and that basically by applying the concept of the subjective frame of reference to reference frames in general, we were able to calibrate the mathematics that's used in modern physics and apparently resolve an issue which remains to be seen.